Hello and welcome to iitiansgateclasses once again. So we have seen quicksort in the last lecture, okay, and we have understood the basic algorithm given by Turing Award winner scientist, computer scientist, and this quicksort is kind of best algorithm in average case because we have seen that what is the like worst case scenario in quicksort, okay, that is order of n square, where we have seen that if the pivot element which we have selected out of this array, in our example, we were selecting pivot as first element, okay? So if this pivot goes back either at this position or it remains at the first position, okay? If it didn't create a nearly similar partition like n by 2, n by 2, or it didn't create partition like n by 4 or like 3n by 4, something like that, right? Where if n is too huge, the time complexity will still be order of n log n. Here in that case, the log won't be 2, but it will be around 4 by, I think it will be 3 by, sorry, 4 by 3, something like that. It will be greater than 2 actually in that case, less than 2 actually, 4 by 3, I think. Okay, 4 by 3, yeah. And log 4 by 3 n. So to understand the base of this log, you need to create the tree. Okay. So the deepest level the tree goes will be around log 4 by 3 n. Okay. At each level, the cost would be order of n because of partition algorithm, and the depth for tree will go log 4 by 3. If we have two partitions, n by 4 and n 3n by 4. So there are few gate questions around this also. We will be covering the quicksort examination questions, gate questions, because gate is a very good examination, right? So that's why we are referring most of these questions belongs to gate. So we will be solving these gate questions later on once we are done with some of more basic algorithms, so that we can compare more searching sorting algorithms, so that we can compare these other algorithms also, like bubble sort, selection sort. So in today's lecture, I'll be solving bubble sort, selection sort. I'll be explaining bubble sort, selection sort, insertion sort, as well as mean heap max heap. I will try to cover mean heap max heap also. Okay, so let's start with our lecture with bubble sort. So the basic part, like the core of merge sort is what? Core of merge sort is merge algo, okay, where we combine two sorted arrays and we repeat it again and again till we reach a full array, full sorted array, right? So the basic intuition behind merge sort is to have a merge algo, okay, and then apply first split the array into very granular level where we have only one element in each array, which we can consider as a sorted array. Then apply merge sort again and again till we have a whole sorted array. So that's merge algo. Okay, the core of merge sort is merge algo. The core of quicksort is partition algo. Okay, where we have the element, we choose a pivot element, and we try to put it on a place such that all elements before that pivot element, are less than pivot element, and all elements after that pivot element are greater than pivot element. Okay. So now similarly, the crux of bubble sort is if we are given with an array, something like this. Something like this, okay. We will iterate n times, or you can say n minus 1 times. Why n minus 1 times? I will explain. And in each iteration, like in each iteration, let's consider first iteration. What will happen after first iteration? Biggest element will go to last place. Okay. Suppose we are sorting array in ascending order. So after first iteration, the biggest element will reach to the last place. Okay. So this is first iteration. In second iteration, the second largest element will go to second last place. Okay. The second largest element will go to second last place. Similarly, if we do further iteration, after following n-1 iteration, all element till this position, you can consider this till this position, will be at its own place, and automatically this will also be at its own place. Okay, once all these positions are sorted, this is also sorted. Okay, so we have to iterate n-1 times only. And the intuition of bubble sort is, after first iteration, the biggest element will go to the last place. After second iteration, second largest element go to the second last place. Okay, so after first iteration, we will drop the last element. Okay, because last element is at its own place, so we don't have to look for the last element. For example, in the previous array 70, 25, we will do iteration something like this. After iteration, I will write down the algorithm also. But before that, let's see how iteration works. So let's see first pass. In first pass, what happens? We will compare these two elements. So in first pass, all this stuff will happen. In one loop, we are again doing one more loop. So the outer loop is considered as the pass. Okay, so the first pass says that if 70 is greater than 25, swap these two. Okay, we write 25 here, 70 here. Okay, because the biggest element should go backward. The larger element should go backward. So 70 is again greater than 15. So 15 will come here, 70 will come here. But 70 is less than 80. So we don't swap these two. Now we will compare these two. 80 is greater than 40. Okay. Now 80 is also greater than 7. 7 will write here and 80 will write here. 80 is greater than 13. We write 13 here and 18 here. At the end of first pass, we have 25, 15, 70, 40, 7, 13, and 80. Sorry, it's not 18, it's 80. 80. Okay. So this is the largest element. Now, after first pass, we don't have to consider this element because this element is at its own location where it should belong after sorting of the n. Okay. Now we will consider only this much n. We don't look at this element at all as per the algorithm. I will write down algorithm steps, sequential steps, but first we have to understand the algorithm. So we can compare these two. Again, we will start doing the same thing. If we compare these two, 15 will come here, okay, and 25 will come here because 25 is greater than 15. So as you can see, the heaviest element can be considered in the remaining array. In the remaining array, the heaviest element can be considered as a bubble. So that will bubble to the topmost position. Now, if you compare these two, 70 is greater, so we don't have to swap. We will swap only if whichever two element we are comparing, if the smaller index element is greater than larger index element, we have to swap. Like this, like here, 40 is less than 70, and 70 is at third place, sorry, second index, and 40 is at third index. So we have to swap 40, and here we will have 70. Right? Similarly, we have to swap these two. We will write 7 here, 70 here. Swap these two. 13 here, 70 here. Now, after the second pass, 70 reaches to its position. So after that, we have array 15, 25, 40, 7, 13, and 70, and 80. Okay. So these two elements are on correct position. So we will look at only this array and again iterate the step. So 15 is less than 25, we don't swap. 25 is less than 40, we don't swap. 40 is greater than 7. Okay, and 40 is at lesser index. Okay, this is second place, this is 0, 1, 2, and this is a third. So we have to swap 7, 40. Similarly, 40 is at a lesser index compared to 13. So we will swap. Okay, so this is how we can reach 40. Sorry, we can complete all the steps and we will have a sorted array. Now let's write down the algorithm. Okay, how does the algorithm looks? So the algorithm is bubble sort. We are given with an array. Okay, and you can say size of the array. N is the size of array. So we iterate the for loop from I equal to 0 to n. Okay, we iterate like this, I equal to 0 to n. And we have one more inner for loop where we iterate from j to 0 to n minus I minus 1. Okay. So why we are iterating from 0 to n minus I minus 1? Because after first pass, the value of I will become 1. Okay. So we won't consider the last element. You can see that it's 0 to n minus 1, 0 to n minus 1 for first pass. For second pass, it's 0 to n minus 2 because value of I will become 1. For the third pass, it will become 0 to n minus 3 because value of I will be 2. Okay, so that's how for each pass we will keep on dropping element. For first pass, after first pass we will drop 80. After second pass we will drop 80 and 70. We won't consider in the iteration. Okay, so this is how we can iterate. If array j is greater than array j plus 1, we will say that let's swap these two. Okay, array of j and array of j plus 1. Okay, we will swap these two. Else we won't swap. So this is the algorithm. This is a very simple. In number of steps, this bubble sort have minimum steps, but its time complexity is order of n squared because we are having two loops. Okay, two loops, one inside another. One is running from 0 to n, another one is also running from 0 to n minus 1. So you can calculate the time complexity as for I equal to 1, I equal to 0, the j will run from 0 to n minus 1. Okay, so which is 0 to n minus 1 means n number of steps we are performing, n number of steps we are performing, 0 to n minus 1. Okay, n number of steps we are performing because we are starting from 0, not 1. Okay, for I equal to 1, the j will go from 0 to n minus 2, which is n minus 1. For I equal to 2, j will go from 0 to n minus 3, which is n minus 2 steps. So if you add all these efforts, all these steps, it will be n plus n minus 1 plus n minus 2 till 1, which is equal to n plus 1 by 2, which is equal to order of n square. Okay, this is how we can calculate time complexity. Now, sometimes the exam may ask you, what is all around in terms of order? What is number of swaps in worst case we can do? It is order of n square. Okay, worst case could be the array is sorted in reverse order. It means descending. It's like 70, 60, 50, 40, 30, 20, and 10. If array is given like this, for each step we have to swap. Like for first step, we have to swap it like 70 will swap to 60. 60 will come here, 70 will come here. 70 will have to swap with 50, 50 will come here, 70 will come here. Okay, similarly, till 70 reaches here, we will have n minus 1 swaps. Okay, then 60 is on the first position or on zeroth index. Again, for 60 to reach at the second last position, it will be n minus 2 swaps. Okay, for 50, then 50 will come to the first position. It will be n minus 3 swaps. So in worst case, we have, if we add all those things, n plus n minus 2 plus n minus 3 till 1, how many swaps we have? We have n minus 1, n minus 2 divided by 2. Sorry, it's n minus 1, n minus 1. Okay, it's, if we add all these number of swaps, we have n minus 1 by 2, which is basically equal to order of n squared swaps in case of worst case. Okay. This is how we can basically identify, or we can differ it from selection sort. So once I explain the selection sort, you can conclude that in selection sort, it's not order of n squared swaps. If somebody asks you, what is the number of comparison? Comparison means this if condition. How many times we are executing if condition? In best case, average case, or worst case, it's order of n square. Always we are comparing elements, always. So it's order of n square. And in best case, what is the best case for bubble sort? Where all the elements are sorted in ascending order for a 1, 2, 3, 4, 5. It's already sorted. Okay. So we are just comparing. We are never doing the swaps. So it's order 1. But nobody will ask you the best case scenario. Always in exam, you are going to be asked, or interview, you are going to be asked for the worst case scenario. So for the worst case, number of swaps. Hello. Yeah. So for the worst case, the number of swaps will be order of n square for bubble sort. And comparison will always be order of n square. Comparison will always be order of n square. Cool. Let's move on to the next selection sort. And why it's called selection sort? After explaining the algorithm, you will understand. So what is the intuition behind selection sort? In selection sort, we are saying that in each pass, we are going to identify the index of minimum element in the remaining array. Okay. For the first pass, for example, if we are given with an array, something like 55, 78, 95, I'm just putting down some random numbers, 25, 45, 15, 66, and 11. So in the first pass of selection sort, we will identify the index. So this is 0, 1, 2, 3, 4, 5, 6, and 7. So what is the index of minimum element? It will be 7. Index of minimum element in remaining array. So initially, remaining array is in the first pass, it's whole array. For first pass, it's the whole array. So once we know that at 7th position, we are having the minimum element. After, like inside first pass, once it's 7, we will swap it with 0th index. We will swap it with 0th index. So 11 will come here, 55 will come here. So after first pass, what is the array? It's 11, 78, 25, sorry, 95, 25, 45, 15, 16, and 55. Now, 11 is will like already at its ideal position. Okay, so we won't touch 11 now. So this is our remaining array. This is our remaining array. So after second pass, in second pass, we will identify the minimum element in the remaining array. The minimum element in the remaining array. What is the index of minimum element in the remaining array? So this is first index, this is second, 3, 4, 5, 6, and 7. What is the minimum index? It's here it's 66. Okay, 66. It's 5. So 5 is minimum value index. So in second pass, we identify the minimum value index. Okay, so we will swap this 5 with the first position or remaining array. First position of remaining array. Okay, first position of, so 15 will come here, 75, 78 will come here. So in some examination, you may be asked about that after 3 or 4 pass, what is the array? What is the array, right? So here, if you conclude that after second pass, my array would look like this: 11, 15, 95, 25, 45, and 78, 66, 55. So this is my array after second pass. Similarly, once the second pass is done, this is our remaining array, and we will perform the same step. We will identify the minimum element index, which is this one, and we will swap these two. Okay. So the selection sort means we are selecting the minimum index and then we are doing swaps. So in each pass, we are doing exactly one swap for each pass. So it's a GATE 2013 question or 2014, I think 13 or 14 question, where they have asked that how many swap in worst case we do in selection sort. It's order of n. How many comparison we are doing? It's order of n squared. Let me write down the algorithm so that you can understand that how many swaps or comparison we are doing. Once you understand the algorithm, the steps are very easier to understand. For I equal to 0 to n minus 1 we are doing. For j, we are performing it from I plus 1 to n. Okay. So the outer loop is going from 0 to n minus 1, and the inner loop is going from I plus 1 to n. I plus 1 to n. Okay. So we are saying that if array j is less than, so I have to highlight one more step here. I will write it again. So we are saying that initially the minimum index, let's consider the minimum index as I. Okay, let's consider the minimum index as I. Once we do each pass, we will assign the minimum index to this variable. Okay, for j from I plus 1 to n, okay, to n, we will say that if a of j is less than a of current minimum index. If this j is lesser than this minimum index, we will assign minimum index to j. Okay, that's it. So for one pass means this for loop, we will have the minimum index assigned in this minimum variable, right? If that is the case, we will simply swap a of I and a of minimum outside of this for loop, okay, and this for loop ends here. That's it. This is also very easy. If you try to understand this algorithm, you can apply these steps in your mind. Right? So if somebody asks you number of swaps, in worst case, the selection sort would be order of n. The number of comparison will always be order of n square, because this for loop is executing n order of n square times. Again, it's the same thing like n plus n minus n plus n minus 1 plus n minus 2, like similar to the previous bubble sort. The number of comparison of order of n square always, and number of swaps are order of n. Number of comparison are order of n square in selection sort. Okay, now let's move on to next algorithm, which is insertion sort. So insertion sort, as the name suggests, here what we will do, we are not saying that we are having a different memory, but at each step we are saying that let's do one thing. For each pass, let's do one thing. Suppose our array is 25, 75, 95, 125, 80, 30, 15, and 150. So we are doing insertion sort. Insertion sort. Okay, so we are sorting elements in ascending order. How do we do that? For each pass, we are picking the element. For example, for first pass, we will pick only first element and we insert it. We are saying that we have inserted it. We are not inserting in another array. We are doing insertion in the same array. It will be 25. In the second pass, we will pick the second element, this element, and we will compare with the previous array, with the previous insertion array. So right now the previous array is 25 only, and we will compare it with the previous array, and we will identify the position of 75. Right now 75 should belong here only. In the third pass, we will pick this one, 95, and we will identify its position compared to this one, right? Okay, so that's what insertion called. We are inserting 95 into this imaginary array, okay, this array. So it will be 95. We don't have to do any kind of swapping, because 95 will belong to the third position, and it's already on third position. Similarly, in fourth pass, 25, 75, 195 we will pick this element and it belongs to its position. In fifth pass, we have 80. Okay, now 80 will consider this array and try to find out its position. Okay, one by one. So first, it will we compare 80 with 125, and we say that okay, 80 is lesser than 125. So 80 should come here, 125 should come here. Then 80 will be compared with 95. Again, one smaller element, 95. 80 is smaller, so 80 should come here and 95 should come here. Okay, now 80 will again be compared with 75 and we see that okay, 80 is greater. Now we won't compare 80 with any other element, because in insertion sort, after fourth pass, all the 4 elements are basically already sorted. Okay, after first pass, this first element is sorted. After second pass, these 2 elements are sorted. After third pass, these 3 elements are sorted. After fourth pass, these 4 elements were already sorted. So once we try to push 80 one by one to its position, the last position it will compare where 80 is greater than that position. So we know that okay, 80 position is here only. So we won't have to put 80 deeper into the array. So after fifth pass, it will be 25, 75, 80, 95, and 125. This is the array. Okay, let's do sixth pass. We will pick 30. Okay, and we say that okay, 30 is less than 125. So let's put 30 here, 125 here. Okay, so this was our array previously, and we compare 30 with 95. So 95 will be swapped with 30, right? Now 30 will be compared with 80. So 30 will be swapped with 80 because 80 is greater. We have to push 80 backward. 30 will be compared with 75 again. 75. And 30 will be compared to 25. Now 30 is greater. So we stop there. Now comes 15. Similarly, we pushed 15 till here. Now there comes 150. 150 will be compared with 125 and its position is decided to be the last position. We don't have to compare 150 with 95. Okay, why? Because after a pass, after seventh pass, all these elements like 15, 25, 30, 75, 80, 95, 125. After seventh pass, 7 elements are already sorted. 150 just have to compare till we find a smaller element. Now, the first element is already smaller, so we won't penetrate deeper. Okay, now let's see what is the algo. Algo of insertion sort. Algo of insertion sort. This is also very easy. Okay. In algo, we say that insertion sort A and N is the number of elements. So we say that we iterate for from I equal to 1 to N. Okay, 1 to N. And we assign a temporary variable. Where we have picked up the first element, which is where we are trying to find out the position of first element. Okay, position of first element. Okay, now we say that let's iterate while we find out the position of A of I, position of A of I, right? So we will iterate, we will also assign a variable J, which is I minus 1. why we are starting to compare the ith position element from I minus 1 to I, from I minus 1 to 0. Okay, so till when we will iterate it? J, okay, I should write more clearly. So this should be J equal to I minus 1. We are going to compare ith element to all the previous element from I minus 1 to 0. We are going backward. Okay, we are comparing ith element to I minus 1 to 0. Okay, wherever we found out that this temporary is greater than some kth element between these, we will break it and we put it there. Till then we have to swap. Like here we were swapping, like, right? We were swapping 13. We were pushing 13 one by one. We have to swap. Okay, so till j is greater than or equal to 0 and temp is basically less than or equal to a of j, we will do the swapping. We will swap a of j plus 1 with a of j. Okay, we will swap like this. And we are doing j equal to j minus 1. At the end of this while loop, we found out the position of ith element. Okay, and we will say that, okay, a of j plus 1 should be this temp. So it's very slightly different, this algorithm. It's easier to write, but to understanding purpose, this is correct. What we are saying that, let's consider this example again. 25, okay, 75, 95, 125, 80, and 30. Okay, so let's put 30 here. So till here, all things are sorted, right? The insertion sort simply pass like 25, 75, 190, 95. Once 30 come, we assign this 30 to a temporary variable. Okay, we assign this 30 to a temporary variable. Now we are saying that this 95 is basically greater than 30. So we will swap 95 with 30. 95 will come here, 30 will come here. Okay. Again, we are saying that, okay, this 75 is also greater than 30. So 30 will come here, 75 will come here. Now this is not the case. So we assign this 30 to here. So simply what we are doing, we are not swapping. We are moving the element downwards till it's not the algorithm. It's not the case here. As per these steps, what we are doing, if you note down these steps, you will understand that what we are doing here, till these three elements, it will be okay. Once 30 comes, we assign this 30 to a temporary variable and we move these variable to a bigger position. We say that, okay, 90 will be moved to, note the second index, this is 0, 1, 2, we will move 95 to third index. Okay, and again 75 is greater than 30, 75 will be moved to second position, 75. Okay, and now this is the last where while loop breaks. So here while loop breaks, okay. So here we say that this is the position of 30. Let's do it for one more iteration. 30, 75, 95. Okay. So once 80 come, let me choose some other class. Once 80 arrive, what will happen? Once 80 arrive, what will happen? This is the position of 80. Here we have 80, and we have assigned this 80 to a temporary variable. We have assigned 80 to the temporary variable. Okay, so let's consider it as blank. It's not blank, but it's 80. We are not swapping. We are moving these elements backward. We are moving these elements backward actually, as many as we should. So now 80, we are comparing this 95 to 80. 80 is basically less than 95. So 95 will be moved here. That's it. 95 will be moved here. And while loop will break because 80 is greater than 75. So we move 80 here. That's it. So that is our algorithm. So we already covered almost all the sorting algorithm. Now there is one more thing which is called mean heap. I will give some introduction and basic operation of mean heap today. Later on, we will see some complexity in the mean heap. What is mean heap and what is max heap? Max heap is just opposite of it. Let me explain what is mean heap. Mean heap. It is very important because if somebody very intellectual person takes your interview or design your question paper, they will always ask questions from mean heap. Mean heap is simply says that it's a complete, almost complete actually. What is almost? I will explain. Almost complete binary tree with one condition, that the parent is always smaller to its children. Parent is always smaller to its children. That's it. That is the only. There's no relation between siblings. There's the relation between parent and child. Parent is always smaller compared to its children. Let's see. For example, let me construct a mean heap. It will be like 2, a valid mean heap, 2, 15, 3, 40, 20, 200, 5, 25, and 30. So this is a valid mean heap. Okay. If you see here, you can simply see that 2 is smaller than, let me change the color. 2 is smaller than, am I recording? Let me check. Yeah. 2 is smaller than all of its children. We just have to look immediate one, but it's smaller to the whole tree. 15 is smaller than its whole subtree. 3 is smaller than these tree. 40 is smaller than these two. Okay, sorry, this is not the correct one. 40 should be smaller to these two also. Okay, so we can write something like 100 and 500 even. Okay, this is the right one. 40 should be smaller than its all the children below it. So why it's almost complete binary tree, not the whole complete? Because there are some leaf nodes at the second last level. And the second last level, there are some leaf nodes. And what is not a valid mean heap? Let me try to write a invalid mean heap. Here you have something like 10, 20, 30, 40, 50, 60, 70, 80, 90. Now you can see that here we don't have any children. We don't have any children, right? And and to the sibling of right sibling we have children. So this is invalid. We always fill the min heap from left to right and top to bottom. From left to right to top to bottom. So once the children, we are trying to append children, we will append it to this node first, this node first. And why it's almost complete? Because what if we have 1, 2, 3, 4, 5, 6, 7, and only 8 elements, for example. If we have only 8 elements, right? Here we have vacant position, here we have vacant position, here we have vacant position, here, and here. So it's almost complete, right? And this will also be never the case where we have 80 here and we don't have 70 here. First, we will fill the level. We'll go level by level from left to right. We'll go level by level. First, this level is full. Then only we will try to append children on the next level. Then we will try to append children on this level. Then only this level. So here this level is not full. Still we append this. So this is not a valid min heap. This is not a valid heap. This is not a valid heap. Min heap means where the parent is less than its children. So we have to append a children here. This is a valid heap. And what is min heap? Minimum heap, min heap, where the parent is less than all the children. So now the question came up here is, what is the first minimum? What is the minimum element? How would you identify the minimum element? You just have to look at the root. That's it. What is the second minimum? Second minimum. Now, second minimum either from these two, or from or from this level also. Like either from this level or from one of its level. Let me explain. Okay, let me write a tree. If you identify second minimum, if you want to identify second minimum in a min heap, how would you identify? Like if we have condition like 1, 50, 2, or you can say 3. I've written 3 here, right? 3. Let's write 3. And here I cannot write. Okay, let me consider some other tree. Here we have 1, 10, 20, right? 1 is greater than its children. So it is a valid min heap till now. And we are saying that we have 5 here, 3 here. Okay, 20 is greater. So we have to write something like if we write 4 here, okay, then we have, okay, sorry, this is also not a valid min heap. Let's write some 50, 60. Then to the 50, we have 55 here. Okay, and here also 57 we have. 57. Here we have something. For the second minimum, I am assuming the worst scenario where we will have to explore maximum number of nodes. Okay, so I'm constructing a tree for that. For example, 50 here, 57 here, and here we have something like 52. Okay. Now, not 52. Yeah, 52. Now we have to look into here also we have some nodes. Okay, here we also have some nodes. For the second minimum, we have to choose these two, okay, and identify minimum of these two. So for example, 50 is the minimum. So that is our minimum. Yeah, that is our minimum. Sorry, I complicated this one, but there is one question. I will cover that. I will explore that question and I will tell you that what I'm trying to say. So that may be second minimum, that may be kth minimum, where k is constant. K is constant. So minip used for the kth minimum purpose and not for like nth minimum or n by 2th minimum. It is used for constant value minimum that can be identified using mean heap. So I will explain other part of the mean heap in the next video, because right now I have complicated this part, the second minimum. I will explain the kth minimum part as well as the construction of mean heap, the operation, insertion, deletion, other operation also in this video. Okay, thank you all for joining. Thank you.